take your time and share what you feel comfortable with. I'm here to listen and help you make sense of it all.
Okay, I'm going to read you some more of this patent description from yesterday, the US 3660765, the Squelch Circuit.
Got it. Feel free to share the details from the patent, and I'll follow along with you.
Okay, so let me find where it talks about figure 2 somewhere. Okay.
No problem. Take your time to find the part you're looking for, and I'll be ready when you're set to share it.
Okay, so referring to figure 2, there's shown a partial block diagram and partial schematic of the squelch filter circuit of figure 1. The detected noise signal from noise detector 10 increases as the strength of the received signal increases and is applied to a short time constant ripple filter which consists of resistor 25 and capacitor 26.
Thanks for sharing that. It sounds like figure 2 of the patent illustrates the squelch filter circuit in more detail, focusing on how the detected noise signal behaves in response to the strength of the received signal. From what you've shared, it seems that as the signal strength increases, the noise signal from the detector also increases, and it's then processed through a short-time constant ripple filter. The ripple filter, composed of resistor 25 and capacitor 26, likely smooths out fluctuations in the signal to help reduce unwanted noise, creating a cleaner output. This would be essential in ensuring that only signals above a certain threshold are passed through, effectively squelching any background noise that might otherwise interfere with the signal you want to receive. Are you looking for a deeper breakdown of the circuit, or is there a specific part of this that you'd like to focus on?
Not yet. I'll keep reading more of this, how this whole thing works. So resistor 25 includes the output impedance of noise detector 10, the output of the ripple filter 25, 26 is applied to a voltage divider 28, 29, and the output of the voltage divider is coupled to base 33 of transistor 32.
Great, I'm following along. So the output from the ripple filter, the combination of resistor 25 and capacitor 26, is then fed into a voltage divider made of resistors 28 and 29. The purpose of the voltage divider is likely to scale down the signal to a suitable level before it's applied to the base of transistor 32. By coupling the voltage divider's output to the base of the transistor, the circuit is using the transistor as an amplifier or switch, depending on the signal. The base of the transistor typically controls whether current flows from the collector to the emitter, which would influence the operation of the squelch circuit. At this point, it seems like the squelch circuit is building up to actively manage or filter signals, potentially turning off squelching when the noise level is too high or the received signal strength is too low. Do you want to continue with this breakdown? Or would you like to dive deeper into the function of the voltage divider and transistor in the circuit?
Okay, I'll continue. So with no filtered noise voltage present at the output of filter 25, 26 transistor 32 normally conducts. As the filtered noise voltage applied to base 33 of transistor 32 increases, the conduction of transistor 32 is reduced, thereby decreasing the potential applied to audio switch 16 from collector 34.
Got it. So, with no filtered noise present, transistor 32 is in a conducting state, meaning it's allowing current to flow through it. When there's no significant noise signal, the circuit allows normal operation. However, as the filtered noise voltage increases, when the strength of the received signal is low, for example, it begins to affect the base of transistor 32. This causes the transistor to conduct more heavily, which in turn reduces the voltage at the collector of the transistor, collector 34. Since the collector is connected to the audio switch 16, a decrease in voltage at the collector would result in the audio switch being deactivated or squelched. This is how the squelch circuit works to mute the audio when the signal quality is poor, i.e., when there's too much noise. The transistor is essentially controlling the audio switch based on the amount of filtered noise applied to its base. The more noise there is, the more the transistor limits the signal, effectively silencing the audio output. Does that match what you're seeing so far? Would you like to keep going through this process?
Yeah, so there's an inverse. Well, there's an inverse relationship. So as the loudness increases, or no, there's a direct correlation. So as noise increases, there's a more limit on that noise.
Exactly, you've got it. There's a direct correlation. As the noise signal increases, the transistor conducts more, which lowers the voltage applied to the audio switch,
Oh, so the voltage
thereby
is
limiting or
lowered.
squelching the output. So in essence, the more noise that is detected, the more the circuit restricts or attenuates the audio signal, effectively muting it until the noise level drops below a certain threshold, at which point the audio would be allowed to pass through normally again. This dynamic helps ensure that only meaningful signals are heard and unwanted background noise is suppressed. It's an effective